Hello everyone, this is Vasishta from Aerobic section. Today I am going to explain topic of vorticity and strain in aerodynamics. So, what is a vorticity? A vorticity is twice the angular velocity, and strain is nothing but energy or strain rate. So, coming to introduction, vorticity. Vorticity is simply twice the angular velocity denoted vorticity by a vector given here, curl v, and the vorticity of a fluid element cannot change except through the action of viscosity, non-uniform heating temperature gradient. As you can see here, the fluid particles are rotating with a rotational outer flow region with a velocity profile and a velocity boundary region with fluid particles rotating on boundary layer. Vorticity is not intuitively identifiable or directly observable. In some cases, the presence of vorticity is actually expected, while in others it is surprisingly absent. This is explained by recalling that it is the local spin of a fluid particle that generates vorticity rather than rigid body rotation of fluid mass, in which particles do not move relatively to each other. So when the vortex rings form at a vortex rings at wingtips, we can say that the angular velocity of a wingtips with the vorticity can be determined by this vorticity formula. So for a two-dimensional flow in xy plane, the vorticity vector always points on z or minus z directions. In this illustration, the flag-shaped fluid particle rotates in counterclockwise direction as it moves in the xy plane. Its vorticity point is positive z direction as shown. As you can see in this xy plane, the vorticity is placed upwards with an counterclockwise direction. The counter plot of a vorticity field due to flow impinging on a block as produced by CFD calculations. Only the upper half of is shown due to symmetry, and light regions represent large positive vortices. As you can see in this diagram, the flow of block with symmetrical plane is also shown with vorticity here. And description of vorticity. The angular velocity of element about the z-axis in this case is defined as average angular velocity of sides AB and AC, which is Wz is equal to 1 by 2 of d theta 1 by dt plus d by d theta 2 by dt is equal to half dv by dx dou v by dou x minus dou u by dou y. The same analysis in this xy and yz plane will give a 3D elements angular velocity wy and wx. Wy is of dou u by dou z minus dou w by dou x, where wx is equal to of dou w by dou y minus dou v by dou z. And we can see here these three angular velocities are the components of angular velocity vector, where w angular velocity w is equal to omega x I plus omega y z plus omega z k. However, since 2 omega x appears most frequently, where twice the angular velocity, it is convenient to define the vorticity vector as simply twice the angular velocity vector. As you can see, vorticity vector is equal to twice the velocity vector, where that is equal to dou omega by dou y minus dou v by dou z I plus into I plus dou u by dou z minus dou w by dou x j plus dou v by dou x minus dou u by dou y k. The components of the vorticity vector are recognized as the definition of curl of V. Hence, we have vorticity is equal to delta into V, velocity vector. Vorticity vector, which is the components of the vorticity vector are recognized as definitions of curl of V. Hence, we have vorticity vector is equal to delta into V bar. Two types of flows cannot be defined: rotational flow and irrotational. Here, delta delta into V is not equal to zero at every point in the flow. The fluid elements move and deform and also rotate. Irrotational flow. Here, delta and V is equal to zero at every point in the flow. The fluid elements move and deform, but do not rotate. The figure contrasts the two types of flow: rotational flows, irrotational flows. Strain rate. Using the same element side angles, we can define the strain of fluid element. Strain is equal to delta theta 2 minus delta theta 1. This is the same as strain used in solid mechanics. Here, we are more interested in the strain rate, which is then simplified. D strain by dt is equal to epsilon xy is equal to d delta t2 by dt minus d delta 1 delta theta 1 by dt, that is equal to dou v by dou x plus dou u by dou y. Similarly, the strain rate rates in the yz and zx plane are epsilon yz is equal to dou w by dou y plus dou omega by dou y plus dou v by dou z. Epsilon zx is equal to dou u by dou z plus dou omega by dou x. And in strain rate is the rate of deformation caused by strain in a material within a corresponding time. This gauge the rate where distances of materials change within the respective period of time. It involves both the rate wherein a certain material expands and shears, make it a standard measurement in the analysis of the corrosion process. Whereas Whereas the strain rate at some point within the material measures the rate at which the distances of adjacent parcels of material change with time in the neighborhood of that point. It compromises both the rate of which the material is expanding or shrinking, which is expansion rate, and also the rate at which is being deformed by progressive shearing without changing its volume. It is zero if these distances do not change, as happens when all particles in some region are moving with same velocity, same speed and direction, and are rotating with the same angular velocity, as if that part of the medium were a rigid body. The definition of strain rate was first introduced in 1867 by American metallurgist J. Lecoq, where defined who defined it a rate at which strain occurs. It is time rate of change of strain. In physics, the strain rate is generally defined as the derivative of strain with respect to time. Its precise definition depends on how strain is measured. Then, vorticity and strain rate. Fluid element behavior on vorticity and strain rate, where when previously examining fluid motion, we consider only the changing of position and velocity of a fluid element. Now we will take a closer look and examine the elements changing shape and orientation, considering moving fluid element which is initially rectangular as shown in figure. In the velocity varies significantly across the extent of element. Its corners will not move in unison, and the element will rotate and become distorted. This is all about my explanation on vorticity and strain rate. Thank you.